By the way, one of last week's recordings did something weird where it got recorded to an earlier meeting. So you have to skip to like the second recording. It works though. I checked and it works. I think I just had too many devices on Zoom all at once.
The Thursday class or the Tuesday class?
I think it was the Thursday. Was it?
It was Thursday.
Yeah, okay. Okay, I'm glad you guys are checking the recordings. That makes me feel good about myself. Did the weekend go okay? Homework get done? Quizzes, work? Okay. Then this week we have a kind of straightforward chapter. It's over capacitors. So we're about to start circuits. And so we're starting with capacitors and we're going to talk about them more as like how will this work when you attach actual wires and a battery up to a capacitor. Next week we're going to start talk about current and resistors. And then after that we're actually going to get to like let's hook it all up and figure out how this circuit is going to work. So there's much more of a application. It's much more of an application-based chapter.
Is that all theoretical, or are we going to hook it up to like a breadboard?
We are totally going to hook it up. You don't get a breadboard until another year or two. You get alligator clips now. Too much. You guys might hurt yourselves. But yeah, you will, get to light up a light bulb in the coming weeks. It's great. But okay, so for now, we are doing capacitors, and so let us discuss how a capacitor works. Okay, and I should chat up. Okay. Whatever chapter this is. Actually, is this chapter 8?
Yeah.
Thank you. Chapter 8. Capacitors. Okay. So, in the very impractical sense of the word, which is to say the physicist sense of the word, the way we use capacitors is to generate electric fields. You might have noticed this because throughout the last couple of weeks, we've been like, hey, check out this nice straight electric field that's uniform magnitude over a distance. And we said, well, the way to make that is to make a parallel plate capacitor. And so in that idea, that's kind of what you might think about capacitors as a way to generate electric fields. More practically, when we generate electric fields, these electric fields store energy. So there is an energy in electric fields. And let me just stop and say, if anybody wants a mask, they're right there. Please help yourself. Thank you.
To be crushed.
That's why I have extra. And that's really so this energy storage thing is really what you should start thinking about capacitors as, where the way capacitors are going to store energy is by collecting charge and the charge's relation to its potential difference. So this is a definition of capacitance, where the capacitance of a system is equal to the amount of charge it has on it divided by the potential difference that generates. Yeah, so the more charge that you can pack into a system, the more energy that you have in that system. Now, what's one obvious problem with putting too much charge in one place?
Polarization.
Polarization. That's definitely going to be an issue. What if you have a storm with a bunch of clouds rubbing against each other and building up tons of charge? What's going to happen eventually?
Charge a leak.
That it won't dissipate.
That's not what we're going for.
Yeah, it will arc, right? When the potential difference between the ground and the clouds gets high enough, then there'll be a strong enough electric field down to the ground. And where there's an electric field, there's an electric force. Right? So as the potential difference builds between the clouds and the ground, this electric field becomes stronger as well, because remember, electric fields are potential difference over displacement. And so as the charge gets built up in the clouds, energy is being stored up there. You know, like the energy from clouds moving around, so kinetic energy gets started to get stored in electrical energy until you break your system, until the air breaks down, until something arcs, until something melts. So when we say capacitance is charge over potential difference, we're saying the more charge you can pack into one spot while keeping the potential difference lower, and therefore the electric field lower, therefore the electric force is lower, the more capacity you have to store energy. Sound good so far? Okay. Some basic things about capacitance. So units, charge, that's coulombs. Potential difference, that's volts. We use farads to talk about the capacitance of something, where 1 farad equals 1 coulomb per volt. And that's just what we're going to define it to be. This is definitely a scalar quantity. Something either has capacity or it doesn't have capacity. But you want to think about that capacity being in a particular direction. Okay, what else do I need to tell you about this? One particular thing. I'm going to come back to that. Let's move on to an actual capacitors. Okay, so by the way, just burn this equation into your head. We're going to use it all semester. It's a big one. Okay, so first, let's talk about actual capacitors, and by that I mean let's talk about bad capacitors first. One somewhat bad capacitor you might think about would be a single spherical conducting metal, single spherical conductor. So just like a metal ball. So like if I had a metal ball, and let's say it had some charge Q. Let's give it a radius A, just so we have something to talk about. I might want to talk about the capacitance of this. And here's the thing. If you have charge and voltage, the thing has a capacitance. So like every charge generates some voltage, every single charge. So anytime you have a charge, you can talk about the capacitance of that system. They might not be great at storing energy, but you can still talk about it. Okay, so looking at this, we can figure out the voltage right at the surface. And I feel that we did this last week, where the voltage of the surface at the surface of that conductor was KQ over A. Is that okay? Okay, cool. And then we need some other surface because we need a potential difference, right? So we need some other difference. It would be really useful to have the other surface have a voltage of 0. So like voltage 1 being that and voltage 2 being 0. Where would you put a surface? So like imagine your featureless void. You have your metal ball charge Q. It's got a potential to it. I want to look in a place where the potential is equal to 0. Where should I look? Should I look close to my metal ball or far away from it? Away, yes, very far away, right? Because this potential is going to fall off as KQ over R, and only when R goes to infinity, so only when this surface out here is at infinity, will we have this 0 voltage. Okay, cool. Well, let's figure out the capacitance of the system. Well, charge is Q, and then my potential difference would be the difference between V2 and V1, right? And the minus sign here doesn't really matter. You're never going to have a negative capacitance. So it's not even like energy where you could have more or less energy. It's just you have a capacitance. So we have KQ over A minus 0. What's going to happen to those Q's? They're going to cancel out. And so now you have 1 over K over A, or you have A over K. And a lot of times you're going to see this written where K is 1 over 4 pi epsilon naught. And so this is really 4 pi epsilon naught times A. Okay, so that is the capacitance of just a metal ball charge Q, radius A. Yeah. Okay. Now, as you guys might have noticed, this is not a practical capacitor because for this to work, you have to put your potential difference out at infinity. And that's not really going to fit into your lab very well. So this is where parallel plate capacitors are going to come in. And let me say, parallel plate capacitors actually are not usually the most useful capacitors. Usually you see cylindrical capacitors, and you've probably seen them at some point in your life, where they're just wires, where there's like an outside and then like an inside to them. So like an outside and inside surface. And so that's the outside's at one potential, the inside's at another potential, and that way you have your potential difference and you can hold charge on it. So that's actually the most common capacitor that's actually used. But it's definitely more complicated than our very nice parallel plate capacitor. And so the parallel plate capacitor is what we're going to use. So let's talk about it. So we have our 2 plates. And kind of the beauty of the parallel plate capacitor is its nice uniform electric field. That's what we really like about it. Trying to draw two parallel plates. Okay. Generally, we think of this as like one side having a positive charge and the other side having a negative charge, like that. And in the past, when we've looked at this situation, we've talked about the surface charge, the charge in terms of the surface charge density, sigma, where we found the electric field from a infinite sheet, right? And then we said, okay, well, if we have two infinite sheets right next to each other, the total electric field in the center would just be twice that. And that's where we ended up with sigma over epsilon naught. Sound okay? Okay, so this is, we're gonna keep this in our head. This is the electric field of a parallel plate capacitor, where sigma is the charge over the area. Excellent. Okay, now we can definitely use all of this and think of the capacitance of this in terms of the charge on the plates divided by the voltage between the plates. And that would tell us the capacitance of this parallel plate capacitor. However, when we're thinking of that, one practical thing we might want to think about is we are actually going to have to build one of these things. And so if I say I want a 3 microfarad capacitor, it's not going to be useful to try to build a capacitor based on just, okay, there's charge and potential difference. Because if you did that, you'd have to build the capacitor, put some charge on it, measure the potential difference. It would be a pain, right? You'd much rather say, okay, I need to know how big the plates are, and I need to know how far apart to put them, and things like that. So what we need to do with this is we need to say things like, okay, I need to be able to build a parallel plate capacitor with dimensions such as the area of the plates and the distance between the plates. That way I don't have to build something and put charge on it every time I want to figure out its capacitance. Seem reasonable? Okay. Now, of course, we're going to start with the only equation for capacitance that we have. And let's go from there. Okay, so capacitance, charge over delta V. Well, we know that we can relate our delta V to the electric field, which is nice because we know what the electric field of a parallel plate capacitor is. So let's look at that. So if the electric field equals delta V over delta X, that means the change in voltage equals the electric field times delta X. Looking at this picture we have of our parallel plate capacitor, what is our delta X?
The L.
Yeah, that's supposed to be a D, but yes. Because that's the distance the electric field stretches over. Okay, so this is really E times D. Excellent. Also, interesting, the electric field, as we said before, is sigma over epsilon naught. So let's plug that in, sigma over epsilon naught, where sigma is charge over the surface area of the plate. Sigma is the charge density. So that is Q D over A epsilon naught. Does that sound okay? Okay, so remember that is the potential difference right there. And so we're going to take this and we're going to plug it in right there, where you have Q over QD over A epsilon naught. And what's happening to those Q's? Perfect. Which is good, right? Because we didn't want the Q's on it. We just wanted the dimensions. Notice the area is and epsilon naught are going to jump to the top here. And so we're going to be left with a really kind of straightforward equation, parallel plate. Yes?
Just to make sure epsilon naught is a constant, right?
Yeah, it's the permittivity of free space, which tells you how easy or hard it is to get an electric field into an area.
So is there not like an exact number for it?
Yeah, it's 8.85 times 10 to the negative 12.
Then do we just use that to find the free space and everything?
Yeah, and actually I do want to talk about that for a second. I'm going to circle back in just a second to that. That's a point I want to talk about. But first, okay, so looking at this, let's talk about what this means. And let's look at the D first. So the D is the distance between the plates. And so when you're bringing the plates closer together, what's happening to your capacitance? Is it increasing or decreasing? Increasing, good. Because what's happening when you bring the plates closer together, you're increasing the electric field. So remember, electric field is change in voltage over change in space. Now the voltage between the plates is going to remain the same when you move the plates around because that depends on how much charge they have on them. But when you bring them closer together, you drop this delta X, and so you have the same difference in potential, but now over a much smaller length. So your electric field goes up. And remember, we started this saying that electric fields store energy. So the closer you can get those plates together, the more energy you have stored on them. Okay, I like that. And then we're looking at the surface area here. So looking at this, do you want, I don't know if I have much to say about it. You want bigger surface areas. Okay, I do have something to say about that. Bigger surface areas, if you have the same surface, you have the same charge density, more area means more charge. And so you got more charge on there, means you have more energy in your system. Okay, but then I want to talk about this epsilon naught. Because right now you're thinking of these two parallel plates, right? I basically have two sheets of metal and I have air between them. And so when we call this the permittivity of free space generally refers to a vacuum, but electrically air and vacuums are pretty similar. So we can go ahead and just say that that works for air as well. However, let's say I build my parallel plate capacitor. I start shoving charge on there. What is eventually going to happen? Gonna arc? Gonna do that? Yeah. So we'll end up in the same place. So if I want to be able to put as much charge as possible on here, it would behoove me to put an insulator between my two plates, right? And so generally when you build a capacitor, you don't leave air between the two plates. You put some sort of insulator between the two plates. It's both structurally sound and electrically advantageous. And so let's talk a little bit. So that's called a dielectric. Dielectric. Where dielectric is a fancy word for insulator. Yeah, it's just a fancy word for insulator. You describe a dielectric by a kappa. Dielectric constant. Where you just look that up. So like the kappa for a vacuum is 1, The kappa for air is almost 1, which is why we say it's close enough. And so, and then I should say, the kappa whoosh for insulators or dielectrics, insulators is always going to be more than 1. Where if you have some voltage in air, and then, so if you have your parallel plate capacitor and it's got some voltage in air, and then you put a dielectric in between your 2 plates, basically you divide that voltage by kappa. Okay, cool. What that gives you is now your capacitance, which was Q over delta V in air, is now Q over delta V in air divided by kappa. And if you bring that to the top, you have kappa Q over delta V. Or K times the capacitance that something would have in air. And by K, I do mean kappa, not K. Anthony, just so you know, that is Q over delta V. And well, where V is voltage. Thank you, Brian. Okay, so basically by putting a dielectric in between your plates, you increase your capacitance by a factor of kappa. And that kappa is just the kappa of rubber or the kappa of wood or something like that. Which means if you have this, you can also go ahead and throw just a kappa in front of that for whatever dielectric you're going to put in it. And I forget how that relates to what you were talking about, but that's.
Epsilon.
Oh, okay, yeah, where epsilon naught says, hey, we're in air, and so here's what will modify that to take you not into air if you don't want to be in air. Okay, so far so good.
Is that because like it'll cancel out with epsilon, or I guess it's like
It'll combine with epsilon.
Yeah.
So kappa times epsilon naught will equal the epsilon that matches your kappa. So like if this is like rubber, now this is the epsilon of rubber, which is very hard to stick an electric field into. Okay, I like this. Okay, so we have an equation for the parallel plate capacitor without having to think about charge. Let me ask you, if I have just like a parallel plate capacitor like this, and I don't have any charge on it, does it still have the same capacitance?
right? So it has decreasing.
Okay, I like that. Yes, it does. Same. See? Yes. Okay, so even though our equation, like our basic definition for capacitance is charge over potential difference, if you have an object without any charge on it, it'll still have the same capacitance as it did before. The classic analog is in a storage room. So like if I rent out a storage room, it's got a certain amount of cubic feet in it, right? And whether I fill it with stuff or I don't fill it with stuff, it still has the same amount of cubic feet. So my capacitor has this amount of capacitance. Whether I've put charge in it or not, that's still its capacity to store charge. And everyone looks pretty happy with that. Okay, good. Okay, if everyone's happy with that, I would like to do some derivations. Okay, so you have some idea of capacitors, what they are, how they work now. Now I'd like to talk about what sort of things you're going to need to know to put them into a circuit. And the main thing you're going to need to know when you put them into a circuit is how will they combine. So if I have more than one capacitor and I put them together, what will the overall capacitance of the system be? So really quick, let's just like throw down some symbols so I don't have to try to draw parallel plate capacitors. So anytime you just have like a line, that's a wire. Consider them perfect conductors. The two parallel lines, that's a capacitor. Your battery will have one long line and one short line, where the long line will always refer to the positive edge of the battery and the short line will refer to the negative. This one's, you could see this one, switch, yeah. And then the last one that you might see is this, which we talked about earlier this semester. That's ground. So anytime you have a couple of lines that go get smaller, that's ground. And one thing to just keep in mind is that ground has a potential difference of 0. That's why everything will always go towards it, because it'll be the lowest potential just by definition. Okay, given that, there are two different ways, basically, that you can combine these elements. You can combine them in parallel, or you can combine them in series. These are exactly what they sound like. If you are in series, you might have capacitor 1, and then right after it, have capacitor 2. If you are in parallel, you will either have capacitor 1, or you will have capacitor 2. For those CS majors, notice the logic speak right there. It is absolutely a thing. And the definitions you should think when you think about these. Is that a question I need to answer over there? Oh, yes. So to be grounded means you have a connection directly to ground, so you have one spot on your circuit where you know the potential is equal to 0. And that's generally what you use it in your circuit for. If you want, instead of trying to hook something up to both ends of the batteries, if you go from a somewhere positive voltage to ground, you know current is going to flow from that positive voltage down to ground. And so it's a convenient way to draw your circuit sometimes. We're not going to do it in this class, but in all of your engineering classes, you're going to do it. Okay, what was it? Oh, yes. We want to define these things. Okay, so for series, it's important that everything that goes through one also goes through 2. So 2 things cannot be in series unless every single object, every single charge that goes through one also goes through 2. For parallel, nothing that goes through one can go through 2. Nothing that goes through one can go through 2. Okay. There are totally situations where you might find yourself in where things don't fall in neatly into one of these 2 categories. For those situations, we will address some of them maybe even today. You have to think a little harder. But to say something's in series, you have to be able to say confidently that everything that goes through one also goes through 2. And for things that go in parallel, nothing that goes through one of them can go through the other one. Sound okay? Okay. Then let us, oh yeah.
So but then the original.
Uh,
So like for parallel, there's nothing I go to C1, but at the end.
so let's say I have like some happy little charge that's going through my circuit. It hits this T, right? It can choose up or it can choose down, but it can't go through both. Yeah, so it'll go this way, and maybe there's some other charge that will choose the other direction. But the green charge that goes through C2 is now never going to go through C1. Okay, good. Okay, so here's let's start with parallel because it's easier for capacitors. Parallel. The idea with two parallel capacitors is I want to be able to take these two capacitors and I want to simplify it down. I want to say, okay, what if I just had one capacitor with the equivalent amount of capacitance as these two capacitors in parallel? So that would make my life easier if I knew that. And so what we need to find is an equation that connects C equivalent to C1 and C2. So let us draw a circuit. Let's draw a circuit. So I have a battery over here where I have some battery voltage right there. Generally, we say the negative side of the battery is just 0 voltage. So, for example, your battery could go from positive 3 volts to negative 3 volts. You'd have a potential difference of 6 volts, right? But it would be much more convenient if instead of positive to negative 3, it just went from 6 to 0. And so just for convenience, instead of saying positive and negative, we just say the potential difference is 6 volts. Let's put it starts at 6 volts, it goes down to 0. Sounds okay? Because it's really the difference that matters, right? The difference is what's going to make the electric field. That's going to make the electric forces. If you're just going from like 200 volts to 201 volts, you're really not going to see a lot of electrical activity because you only have a potential difference of 1 volt. That's, I don't know, a little bit less than a AA. I would like to also point out that that's a bit of a dangerous situation and why we have ground fault interrupters on all our big appliances. Because at some point, if you manage to hit ground and you're up at 200 to 300 volts, you're immediately going to be shorted into ground. And so it'll stop saying, hey, this is the difference between 200 and 201. And it'll start saying, hey, this is the difference between 200 and 0. Does that make sense? Our battery, though, does not have that problem. You don't have 200 volts on the battery. Okay. Okay, so we start off here. We have C1 and we have C2. Now let's talk about this. All the straight lines are just wires, and they are perfect conductors. Can you have an electric field inside of a conductor? Let us talk about this. I'm so glad I asked. Let's say I have a metal ball, and I dump a whole bunch of charge into my metal ball. What's going to happen to that charge? It's going to spread out. Okay, so and this will take nanoseconds, if that. There might be some transient current and fields in here, but almost immediately this charge will go to the outside of my metal ball. Then let's say I want to figure out the electric field inside this metal ball. Because, you know, like I'm looking at this and I'm thinking maybe these charges will like put out some sort of weird field. I don't know. So I go and I think about Gauss's law, where Gauss's law says the flux through a surface equals the charge enclosed by my surface divided by epsilon naught. And so I make a surface, and I'm going to make a surface just on the inside of these charges, which remember, these charges are right on the surface of my metal. And so I'm going to make my imaginary sphere right inside of that. What is the charge enclosed inside the sphere?
Zero.
It is 0. You are correct. Okay, so what is the flux through the sphere? Also 0. And since flux is also equal to E dot A, and there's definitely an area here, so my A isn't equal to 0, what does my E have to equal to? 0. So can there be electric fields inside of conductors? No, that is the correct answer. Okay. Now you do notice, so there was a small caveat there, that initially I dumped the charge in the center and it took half a nanosecond to spread out. Same thing's going to happen when you turn on your circuit. So like say you might have a small switch on your circuit to turn it off and on. Right when you flip that switch, you might have a nanosecond of fluctuations where everything kind of works itself out and the charge goes to where it needs to go. But after that, inside the wires, which are perfect conductors, the electric field has to equal 0. Okay, if the electric field inside a wire is 0, what can you tell me about how the potential changes along that wire? So, in fact, here, let me look at this one. So if my potential difference, so the potential difference, the way your potential changes is equal to the electric field multiplied by the space that electric field is over, and your electric field is 0, what can you tell me about the voltage? Not 0, but I think I heard some constants out there, right? So it doesn't change. The change is 0, right? So that means that along these conducting wires, they're basically equipotentials. The potential is the same as long as you're just dealing with conductors. Sound okay? Okay, so let's say, hey, maybe this battery is 6 volts, so I got 6 volts there. That means right here, I know that wire is at 6 volts. I know this is at 6 volts. I know this is at 6 volts. I know that spot right there is at 6 volts, and I know that spot right there is at 6 volts. Because that's all like the same equipotential. But once you hit those capacitors, now you have a non-conducting area. So I can't just jump over my capacitor and say, hey, it's the same voltage on both sides, because I'm no longer on that conducting equipotential. So I'm going to come at it from the other side, where this is 0 volts, and so that's 0, and so that side of the capacitor is 0, and that side of the capacitor is 0. Believable? So what can you guys tell me about the potential difference of capacitor 1 versus the potential difference of capacitor 2? Same or different? Same. I like that. Okay. the same. So that's one thing we have. What about the charge? And this is where I want you to think about this thing as a parallel thing, where nothing that goes to 1 will go to 2. Can we say the charge on capacitor 1 will be the same as the charge on capacitor 2? No, I like the no, right? And if we have identical capacitors, it will be the same. Because capacitance is charge over potential difference. And if the potential difference is the same and the capacitance is the same, then the charge will be the same. But there's no guarantee that my capacitors are the same. Maybe one's 1 microfarad, then the other's 2 microfarads, right? And so there's a very good chance that the charge on 1 and the charge on 2 are not the same. So far, so good? Okay. But now that we have that information locked down, let's go over and let's compare it to what we might have if we had an equivalent capacitance. So the picture I'm going to draw here is I'm going to have the same battery, but now instead of hooking it up to C1 and C2, I'm going to hook it up to a single capacitor that has the equivalent capacitance of C1 and C2 in parallel. Everyone good there? And what I'd like is I'd like some equation where C equivalence equals some combination of C1 and C2. Okay, and so let's see what we can say is the same. So for example, the voltage across this. I have a battery that's still 6 volts. What's the potential difference across my capacitor? 6 volts, yeah, because I can do the same game, right? I can say, okay, well, everything up here is 6 volts. Everything down here is 0 volts. So whatever is across that capacitor is the same as before. Okay, so there's something I can relate. The other thing I can say is about charge, and this one's a little weirder, where I had charges going through and they were collecting on these plates. Now, they were collecting separately on the plates, whatever collected on 1 did not collect on 2. But for this guy over here to be equivalent, the charge that collected on 1 plus the charge that collected on 2 has to be the total amount of charge that collected on this equivalent. Does that make sense? Because basically I want this capacitor to have stored the same amount of charge as C1 and C2 stored while they were in parallel. Okay, it's all coming together. Let's talk about this guy right here. Okay, where I said Q1 plus Q2 equals Q total. I also have the equation C equals Q over delta V. I can rearrange this as Q equals C times delta V. And in that way, I can take this Q1 plus Q2 equation and start putting in capacitances, because that's what I want to begin with, right? So I have C1. Does it matter if I put like a delta V1 or a delta V2 or anything? No, right? Because they're all the same. So I'm not going to bother with a subscript on my delta V's. I am going to bother with the subscripts on my capacitances. Okay, and what's happening with my delta V's here? Hoping you guys are going to tell me I can just cancel those out. because they're the same, right? And so I end up with a very tidy equation that the equivalent capacitance of C1 and C2 in parallel are just the sum of C1 and C2.
Then why would they cancel out? Aren't they just, it'd be like 2 delta V, or is it like the opposite of the other?
Oh, so I'm just dividing both sides of this equation by delta V.
Oh, I thought you were.
Okay. No, I'm glad you asked. Okay. So that everyone kind of happy with my algebra? Let me say that of course we could have added as many capacitors as we wanted in parallel, and we would have ended up so that they all have the same voltage across them, and whatever charge got distributed among them would still add up to the total amount of charge. So I could certainly say, add up however many of these until you get to the nth capacitor, and it would work. So a lot of times you'll just see that written as the equivalent capacitance is just the summation of C sub I. However, you do need to be very careful that this is only for capacitors in parallel. Okay. Everyone happy with that part? Because if you are going to do capacitors in series. Okay. We're going to go, let's go through the same thing, but now in series. So capacitors in series. Okay. Going to draw a very similar picture, except now instead of one or the other, I'm going to have one, then the other, like that. So I have C1, I have C2, I've got my battery voltage, like that. And I'm comparing it to this equivalent capacitance. Okay, sound okay? Okay, so let's talk about the voltage first. And let's go through the same ideas. So if I have 6 volts right there, I will have 6 volts right there, and I'll have 6 volts up until I hit my first capacitor. Can I say I have 6 volts on the other side of that capacitor?
Yeah.
No. Because inside my capacitor is no longer a conductor, right? I have like a sheet of rubber in there or something. So I expect to have a potential drop across my capacitor. Now, I don't know how much that drop is because I haven't told you anything about this circuit beyond it has a battery. So instead of trying to figure that out, let's start on the other side. That's 0 volts. There's 0 volts. There's 0 volts. Okay, but once again, I run into the same issue that I know that there's some potential difference across this capacitor. I just don't know what it is. So far, so good? Okay. But what I could say is I could say there is some potential difference across C1. And there is some potential difference across C2. And whatever they are, when I add them together, I need to get 6 volts. Because I start at 6 volts, I end up at 0 volts. So whatever drops across 1, then drops across 2, it needs to add up to 6. Is that okay? I'm waiting for a nod from over here. No, it's not okay. It's okay. Okay, so going across the top, as long as I'm on a wire, I'm at the same potential. So if I started the battery at 6 volts, I'm at 6 volts until I hit that first capacitor. I know there's going to be a change in potential across the capacitor. I don't know what it is. And so now I'm going to start at the other side. And so 0 volts at the bottom of the battery, I work my way across. I'm at 0 volts until I hit the second capacitor. Now I know there's another potential difference across that second capacitor. I don't know what it is again. But what I do know is whatever I drop across there and then drop across there, I'm starting at 6 and I'm ending at 0. So whatever these two change in voltages add up to, it needs to be 6. Okay, I got a nod. I'm happy. Okay, so that means the voltage of the battery equals delta V1 plus delta V2. Okay. What can I say about the potential difference across this capacitor? Maybe in terms of the voltage of the battery. So if that's 6 volts and that's 0 volts, what's my voltage across this equivalent capacitor? 6, perfect. So that's equal to delta V equivalent. Okay, excellent. Okay, that looks really good. So that's half it. And now let's look to our charge again. Sorry, just cleaning it up a little. Now, if I look at my charges, we're going to come through, and everything that goes through C1 also is going to go through C2. Does that make sense? That's the definition of series. Any charge that hits C1 is also going to hit C2. So that means that Q1 has to equal Q2. Is that all right? Good, good. And of course, over in my C equivalent, that's going to need to be equal to the same amount of charge as well. Okay, this is good. All right, we're gonna pull the same game where I have the equation I have now is that my individual voltages add up to the equivalent voltage. I want to write this in terms of capacitances. So I'm going to say, well, delta V equals Q over C. And I'm going to take each of these and I'm going to plug them in here and here and here as well. So I have Q over C1 plus Q over C2 equals Q over C equivalent. Where I didn't put subscripts on the Q's because they're all the same. Sound okay? So I'm going to cancel out all the Q's in this equation. Just divide through by Q. And they all go away. And I'm going to end up with a less nice equation as before, but not terrible, of 1 over C equivalent equals 1 over C1 plus 1 over C2. Let me add that I could have put as many capacitors in series here as I wanted. When I did that, I would have to add voltages like that, which would have given me just extra terms, you know, Q over C3, etc. So this is, I can add as many capacitors in series up to C sub n, where 1 over C equivalent will equal the sum of 1 over Ci. This only works for capacitors in series. And so first, when you're looking at a circuit and you're trying to find the equivalent capacitance of something, one of the big things is to identify, are these capacitors in parallel or are they in series? Because you're going to use a different equation depending on which one is true. Is that okay? Okay. The next, with this particular equation, the thing that everyone is going to mess up is they're going to have a bunch of capacitors, and they're going to be going like 1/2 farads plus 1/3 farads, and they're going to come up with an answer, and then they're going to forget that to inverse it at the end. So 1/2, this is 5/6, like that. And they're going to say, okay, my equivalent capacitance is 5/6 of a farad. But it's not 5/6 of a farad, it's 6/5 of a farad, right? I have done it innumerable times. I'm sure everyone is going to do it. But when you have some capacitors in series, just triple check that you inverted your final answer. Sound okay? I think we have time for a problem. Do we need to answer any questions before we do problems, or? So,
theoretical.
I'd love to hear it.
So like the best insulator, like what
Okay.
I'm call the best electric insulator, is that
Uh-huh.
working as like the best, like I guess, like this insulator for like cooling things, like a cooler, would it work the same?
Oh, that is a good question. That is a very good question.
Cool, it doesn't look
So there is something going on here that is actually very interesting, and probably is maybe not absolutely true though for electricity versus heat. So there is a whole lot of overlap between how heat gets transferred between two objects and how electrons get transferred between two objects. For example, metal is really good at transferring heat, and metal is really good at transferring electrons. However, there is this thing with heat where you need a material to carry your heat. So like an electron can exist on its own. So like when you see arcing, those are actual electrons moving around. Heat is actually kinetic energy, where heat is a measure of how quickly molecules, particles are moving. Which is why when you have like the best insulators, what you see that air gap. So like all the fancy water containers have an air gap. And that's because air has very few particles in it compared to metal or plastic or styrofoam even. And so while styrofoam is a good insulator, air gaps tend to be better for heat because there's just fewer particles in there. If you have a vacuum thermos, that's like the best because there's literally nothing to carry the heat from one side of the gap to the other. Does that make sense?
Yeah.
Okay, and yeah, that is kind of the difference. One of the big differences. I guess I've never thought about that too well. I like this question, but yeah, there's so many similarities between electrical and thermal conductivity, but that might be one big difference. That's a good question. Any other questions? Okay. Then I want to look at number 12. Where number 12 is a complicated situation. Not even that complicated, but it's complicated enough that we're going to have to think. Give me a second. I'll get done drawing this. Okay. So this is C1, C2, C3, C4, C5, and C6. Okay, so I have 6 different capacitors. And just so you know, the problem gives you numbers, but let's solve this without numbers. And I would like to find the equivalent capacitance of all of these capacitors put together. Now let me ask you, let's look at C4, C5, and C6. Certainly the charges that go through C4 go through C5 and C6, right? But can you say that all of the charges that go through C4 will also go through C5? I like the no. So given that definition, are C4 and C5 in series? No, right? Okay, they're not in series. Are they in parallel? Do none of the charges that go through C4 also go through C5? No. Okay, so this is one of the situations where two capacitors might not be completely in series and they might not be completely in parallel. When you run into one of these situations, what you have to do is you have to make it simpler. So looking at this set of capacitors, are any of these capacitors truly in parallel?
1, 2.
Those are truly in series, and we're definitely, so C1 and C2 are in series. Check. Anything in
5 and 6 are parallel.
okay, yeah, C5 and 6 in parallel. Okay, so let's go through that. So I know if I add C5 and C6 together, the equivalent of C5, 6 is C5 plus C6. Because to add capacitors in parallel, you just add them up. I know to add things in series, 1 over C12 equals 1 over C1 plus 1 over C2, because that's how you add capacitors in series. This is going to be slightly ugly because it'll behoove us to find a common denominator in here, C2, C1 over C12. And then we need to invert that, right? I'm going to put it over here, and then I'm going to move on to the next page. So C12 equals C1 times C2 over C1 plus C2. Okay, so we made that, we did the simplest thing we could. And so let's redraw this now, where I still have C3, but now instead of C1 and C2, I just have their complete equivalent, right? Like this capacitor acts completely like C1 and C2 would if you put them in here in series. And then I have C4 over here and C5, 6 right there. Does that make sense? Okay, now looking at this, can we say anything is in series now?
4, 5, 4, 5, 6.
Good, okay, so now I will find just the equivalent of 4 and 5 and 6, right? And that'll be 1 over C4 plus 1 over C5, 6. And again, this is one of those things where we're going to say, okay, C5, 6 plus C4 over C4 times C5, 6, and then have to invert it. C4, 5, 6 equals C4, C5, 6 over C5, 6 plus C4. Okay, and for ease, let me redraw this again. So now I have C4, 5, 6. They're all in parallel. Perfect. Okay, so like C total would be C12 plus C3 plus C4, 5, 6. And you would have to go back and add in what C4, 5, 6 and C12 are. But the basic idea is there. You have something complicated, take the simple chunks and break it down, redraw it until you reach the end of something very simple. Okay, everyone seemed pretty happy with that. I might say we can break 5 minutes early. Okay. Here's what we're gonna do. We're gonna break 5 minutes early, but let me tell you what we'll start on next time. Next time we're gonna do number 17 and number 18. And so go home and look at those and think about them in terms of series and parallel. Sound okay? Okay, cool. Oh wait, what did he ask? Oh, he's telling me the answer. Okay, excellent. Thank you, Anthony. Yes, perfect. Thank you, Anthony. That's exactly right.